Good day, everyone. We are Group 7, and today we will be presenting our thermodynamics analysis project on the Vindhyaka Super Thermal Power Station in India. This power station is one of the largest coal-fired thermal power plants in India and operated based on the Rankine cycle, which is an important thermodynamic cycle used in steam power generation. In this presentation, we will discuss the background of the power station, its technical specification, thermodynamic processes, energy analysis, and overall performance. Before we begin, let me introduce our group members. This is me. I am Lee Kevin. Next is Chia Wai Kian, followed by O Kaiser, and finally Moshamim bin Marami. Together, we work collaboratively to complete this thermodynamics analysis project. The Vindhyaka Superthermal Power Station, also known as VSTPS, is located in the Singrauli district of Madhya Pradesh, India. It is owned and operated by NTPC Limited, which is India's largest power generation company. The station started operation in 1987 and has expanded through several development stages. Today, it has a total installed capacity of approximately 4,760 megawatts, making it one of the largest thermal power stations in the country. The power station plays an important role in supplying electricity to northern, western, eastern, and central regions of India. Its strategic location near core reserves ensures a reliable full supply, while its large-scale operation demonstrates the successful application of thermodynamic principles in power generation. Now let's look at the technical specification of the power station. Vindhyaka is a coal-fired steam thermal power plant that uses the Rankine cycle to generate electricity. In this process, water is heated to produce high-pressure steam, which drives a turbine connected to an electrical generator. The plant has a total installed capacity of 4,760 megawatts and uses coal as its primary fuel for continuous baseload power generation. Water required for steam production and cooling is supplied from the Rihan Reservoir. The station consists of 13 generated units, including 6 units rated at 210 megawatts and 7 units rated at 500 megawatts. This unit works together to provide a stable and reliable electricity supply while maintaining efficient power generation through the Rankine cycle. That concludes my part of the presentation. Next, I would like to invite my group member to continue with our presentation. Thank you.
Okay, so my name is Muhammad Shami. So for this slide, I will present about thermodynamics assumptions. Okay, so the following assumptions are applied for the analysis of Vinyachal Super Thermal Power Station. Okay, so for the steady state operation, the power plant operates under steady condition where mass flow rate and energy transfer remain constant with time. For the second one is steady flow process. All components, boiler, turbine, condenser, and pump are assumed to operate as steady flow devices. For the third one is ideal Rankine cycle. Rankine cycle. The steam power plant is analyzed based on an ideal Rankine cycle consisting of boiler, turbine, condenser, and pump. For the fourth one is isentropic turbine expansion. The expansion process in the turbine is assumed to be adiabatic and reversible with constant entropy. For the fifth one is isentropic pump compression. The compression process in the pump is assumed to be adiabatic and reversible. The sixth one is constant pressure heat addition. Heat is added in the condenser at constant pressure until the steam becomes saturated liquid. For the eighth one is negligible kinetic and potential energy changes. Changes in kinetic energy and potential energy are assumed to be insignificant. So the last one is no heat loss to surroundings. Heat losses from the turbine and pump to the surrounding are neglected. Then I will present about Rankine cycle diagram of Winchell Super Thermal Power Station. So as you can see, This is the Rankine cycle diagram for Vinyachal Super Thermal Power Station. Okay, so the Vinyachal Super Thermal Power Station operates based on the Rankine cycle, where water acts as the working fluid in the power generation process. In the boiler, heat energy produced from combustion is transferred to the feed water, converting it into high pressure superheated steam. The steam then flows into the turbine where it expands and converts thermal energy into mechanical energy to rotate the generator and produce electricity. After leaving the turbine, the low pressure steam enters the condenser where heat is rejected and the steam is converted back into liquid water. The condensed water is then pressurized by the pump and returned to the boiler to continue the cycle. This continuous process allows the plant to convert heat energy from fuel into electrical energy efficiently. Okay, next, I will present about net power output and fuel consumption. Okay, as you can see, uh, the table shows the main performance parameters of the Vindiachal Super Thermal Power Station. The plant has a gross power output of approximately 4,760 megawatt, representing the total electrical power generated by the generator before internal power consumption. The net power output is around 4,500 megawatt, which is the actual electricity supplied to the grid after deducting auxiliary power used by equipment such as pumps, fan, and other plant systems. The thermal efficiency of about 35 to 38% indicates the ability of the plant to convert heat energy from coal combustion into useful electrical energy. The remaining energy is mainly lost as waste, heat through the condenser, and other system losses. The fuel power consumption is estimated around 2,000, 12,500 to 13,600 megawatt, which represents the thermal energy input required from coal combustion to produce the electrical output. Okay, so now for page 8, I will present about auxiliary power consumption. Okay, so for the internal loads, auxiliary system consume a portion of the generated power to maintain continuous plant operation and safety. These loads are essential for the thermal power generation process. Boiler feed water pumps and condensate pumps, forced draft and induced draft fans, cooling water pumps and circulating water system, cool handling and edge handling system, control system, lighting, and plant instrumentation. Okay, so for the net output impact, net power output is the remaining electricity after subtracting the power consumed by auxiliary equipment. Reducing internal consumption improve the overall plant efficiency. Gross generation about 4,760 megawatt. Auxiliary power consumption is about 250 to 350 megawatt, about 5 to 80% to 8%. The net power delivered to grid is about 4,400 to 4,500 megawatt, and the net output is equal to gross output minus auxiliary consumption.
Thank you for my teammate Lee Kevin. Thank you for my teammate Lee Kevin. So today I'm gonna present for my slide energy loss and efficiency impact. Stack let loose. Stack gas carry heat away from the boiler and reduce efficiency. So for the energy loss data, you can see stack temperature is 150 Celsius. For the stack loss is 7%, and the heat loss is around 850 megawatt. For the efficiency reduction is 3%. And for the mitigation is air preheater, economizer, and better combustion control. So next one for the temperature profile. You can see from the table for system component, we got main steam, reheat steam, condenser, cooling water inlet, and cooling water outlet. So for the observation, highest temperature occurs in boiler and lowest temperature occurs in condenser. Cooling water absorb waste heat. Next one for thermal analysis. So thermal analysis, the condenser remove waste heat from the exhaust steam after it leaves the turbine. Based on the energy balance calculation, the heat radiation rate is approximately around 3,731 megawatt. This heat is transferred to the cooling water system, maintaining a low condenser pressure and improving turbine performance. Effective heat ration is essential for the stable and efficient operation of Vidyachal Super Thermal Power Station. And last one for my presentation is entropy generation analysis. For irreversibilities and energy destruction, for boiler we got 55%, turbine is 80%, for condenser is 50%, and pump is 12%. You can see here for the pie chart. And second law efficiency is exergy efficiency for 38%, turbine efficiency 88%, and total entropy generation is about 10,000 kilowatt. That's all for me. Thank you.
Environmental impact. The Vindhyaka thermal power station emits substantial amounts of CO2, SO2, NO2, and fly ash due to the combustion of coal for electricity generation. The plant also requires large volume of water for cooling and steam production, which may contribute to thermal pollution and affect nearby water bodies and aquatic ecosystem. Additionally, coal ash deposits can impact soil quality and groundwater if not properly managed. Mitigation and compliance. Flue gas desulfurization system help lower SO2 emission and improve air quality. Water management and cooling system help minimize thermal pollution and reduce freshwater consumption. Operates in compliance with India's Ministry of Environment, Forest and Climate Change, NOEFCC, and Central Pollution Control Board (CPCB) environment standard. Conclusion. The thermodynamic analysis indicates that when the thermal power station operates with a moderate thermal efficiency typical of large coal-fired power plant with major energy loss occurring through condenser heat rejection, fuel gas discharge, and auxiliary power consumption. The analysis highlights that the boiler and turbine system contribute significantly to entropy generation and irreversibility within the Rankine cycle. Improving technology could further increase plant performance while reducing environmental impact. Overall, the study demonstrates the importance of continuous operational optimizing to achieve higher efficiency, low fuel consumption, and compliance with environment regulation. The below is key recommendation. There are a few key recommendations. The first is implement regenerative feed water heating to improve thermal efficiency. The second is adopt real-time flue gas monitoring to reduce state loss and efficiency. The third is optimize boiler and turbine performance to enhance plant efficiency. Future research should explore combined cycle integration and waste heat recovery systems for higher efficiency and sustainability. For reference, we have 7 references. The first is NTPC's Vindhyaka Price Largest Power Generating Station for the economy ties 28 October 2015. The second one is Vindhyaka Coal-Based Power Station. NTPC achieved for the original on 12 April 2018 and repeat 12 April 2018. The third one is Grandon Zelenka David Mitova Stefania 2021 reducing CO2 emissions by targeting the world's hyperpollution power plants. Environmental Research Letter. The fourth is Brigadier Vindhyaka Thermal Station. And the last three is Thermodynamic Textbook. That is all for now. Thank you.